I do not see the red box to tell me that I'm live, but I'm going to assume that I am. So let's go ahead and get started. Thanks for joining me today, everyone. Let's talk about concurrency. So my name is Matt Hawthorne. I'm an engineer on the data-driven journey and messaging platform team, and we're a part of the customer experience org. So disclaimer as we get started today, I'm not a concurrency expert. So if you are here to absorb the wisdom of an expert, unfortunately, you're in the wrong place. But over the years that I've been working in software, I've certainly seen some things with regards to concurrency. So what I'm going to talk about today is some concurrency topics and concepts within the context of projects that I've worked on. So I think one of my overarching lessons today is that comprehension of concurrency, it's really a lifelong journey. There's been a number of times in my career where I felt like I understood something, and then something happened that let me know that I didn't really understand it at all, or didn't understand it certainly as well as I thought I did. It's a process. This stuff is complicated, and so I think that's just something you have to kind of come to terms with and get comfortable with. So my first topic today is on using locks in Java. And I think that this talk was labeled as a programming languages talk. I don't think that's accurate. There's a couple things I'm going to touch on, especially with regards to Java and threads, but this is probably more of a DevOps and distributed systems talk. So let's talk about locks a little bit. With regards to locking, I have two rules. The first one is if you can avoid locking, avoid it. If you have to use a lock, try to make it as fine-grained as possible. And so let's imagine here that we have a hypothetical in-memory key value store, and the data is internally sharded or partitioned somehow. And the question here is, how do you handle concurrent activity to make sure that your data stays consistent? So we're going to go from slowest option to fastest option, and it's also from simplest to most complicated. And so I think the slowest and simplest option here is you just have a single activity lock that allows one concurrent action at a time, so either one reader or one writer. The next option would be to have a single read-write lock, so you can have a single writer or multiple readers at a time. Next up is you could have a read-write lock per shard that allows one writer or many concurrent readers per shard. And I believe this is called lock striping, and this is how a concurrent hash map in Java works. Continuing to turn up the dial, you could have multiple record locks. So imagine like a read-write lock per record, where in the case of a key value store, that would be like a read-write lock per key. Or you could take that one a little bit further, and you could have a read-write lock per key, but you could make it so that if a writer is holding the lock and a read comes in, you could just return whatever the data was prior to that write. So it's kind of like returning stale data, which would be kind of similar to the way that the stale while revalidate HTTP cache control header works. And so there's a bunch of options here. And in terms of weighing the options, I think that if you aren't going to have a lot of concurrency, and if your latency requirements are fairly loose, like you don't have to be, you don't need like single or double-digit millisecond latency, and your write operations are relatively fast, meaning they're not going to hold onto the lock for seconds at a time, I think it's fine just to have a single activity lock. I mean, I know that earlier I said make your lock as fine-grained as possible, but that's kind of assuming that that's one of your performance requirements. I think that having fine-grained locks in a system that only has like 1 or maybe 5 concurrent users, I think that's over-engineering and isn't necessary. But in general, if you find that you do need a higher performance system, you have to be conscious that the more locks you use, the more memory you're going to use. I don't know offhand how much memory a read-write lock takes in Java. It's probably not that much, but if you have 1 million keys or 10 million keys or 100 million keys, that might start to add up. So one thing you could do to mitigate that is you could consider just throwing away the locks after some period of time. I built something similar to this within the last year where it was like a lock per key, and I used a Guava cache that if it wasn't in the cache, I created a new lock and put it in the cache, but then I let it expire after like 5 minutes or so. So that way I kind of balanced that I had a lock per key, which allowed me to be much faster than having a single lock across the whole data structure, but I didn't have to hold on to those locks forever. I think we had like maybe 20 million keys or something like that. Another option here, and I'm not totally sure that this would work, but I think if you had a way to build a unique number or string from your key, if you're doing videos, video/ID, you could maybe just use the synchronized keyword around that and use that as your lock. And you would still have that string object, but you wouldn't have to create a lock object for every one of your locks. So let's move on to the next topic, which is threads and CPUs. I once was debugging an issue with a colleague of mine, and this was maybe like 10 years ago or something like that. And I said, we were looking at a thread dump, trying to understand some things. And I said, once your thread is running on the CPU, it never gets kicked off, right? It just gets to do its work until it's finished. And my colleague looked at me and said, yeah, threads get kicked off of the CPU all the time. That's how computers work. And that was one of these moments for me where I thought I understood something. I thought I understood how threads and CPUs interacted, but I really didn't. And in hindsight, what I said was kind of, I wouldn't call it a stupid question. That's a bit severe, but it certainly was like an uninformed question that just showed that I didn't really understand how things worked. So the way that I think about it is, you can only be actively processing n items at a time, where n is the number of CPUs that you have. And I think typically when we talk about a system in terms of concurrent requests, imagine like a HTTP service, we're including all of the queued processes in that number. So that's not the number of things you're actively processing. In fact, the majority of those concurrent requests are just waiting for I/O. And this is in a, I guess that's true whether it's blocking or non-blocking. So one of the things I ask is, when I'm debugging a system or trying to understand how it should perform to configure it properly, or anything along those lines, is I say, how many CPUs do we have? Because I think that the entire, how you can gauge the amount of work that a system can or should be doing is really, I think, heavily affected by your CPU count. And so, the way I think about a thread is a thread is either waiting or fighting. It's kind of a cruel life, and I'm going to talk about the different phases of threads and CPUs and what I'm calling a typical HTTP service here. And what I'm going to talk about here is blocking I/O. With non-blocking I/O, some of what I'm saying here would be the same, but some of it would be different also, and I'm not going to get into that on this slide. So imagine you have a typical HTTP service. You're taking requests from clients on the left, and on the right, you're sending requests to some other upstream service and then consuming the response. And so step one, request comes in from the client. And let's assume you already have a connection open. So you already have a thread blocking on a socket read, trying to read data from that connection. So I also have a thread queue here. I think that would only be relevant if it was a new connection. I'm not going to talk about that in detail, but I just wanted to illustrate that you might not even have a thread. You might have to, you're waiting even to get a thread, let alone waiting for the thread to get on the CPU. So connections open, you read data from the request that comes in, like the HTTP headers and body, and then you parse that, you use that to build an upstream request to this upstream service. Now you're waiting for I/O from that upstream service. So you're blocking on a socket read again, and you get kicked off of the CPU. And now, once the data comes back from the upstream service, you're reading that data, parsing it, and you use that to build your response that you're sending back to the client. And after that, now you're waiting for more data from that client. So you're kicked off of the CPU and you're waiting for I/O again. And so that's I think a fairly distinct, 4 phases of this request. But even in between, like if you think of a step 1.5, going from step 1 to 2, you're not on the CPU that whole time. You can be on, then you're kicked off, then you're on again. At least that's my understanding of how it works. And this is kind of related to my question a few slides back, that once you're doing work, do you get to stay on the CPU until you're done? And the answer is no. You could be kicked off multiple times between step 1 and 2, and also multiple times between step 3 and 4. And that's just the nature of the life of a thread and how it gets on and off of the CPU. And so in general, the higher that your CPU usage is, the more blips you're going to see in the latency sensitive parts of your application. And so one of the and that's because your thread is basically having to fight for the CPU. And so one of the examples I have here is, I used to work at Netflix. I worked there from 2011 to the middle of 2017. And we had a service there called Cryptex. I did not work on this service, but I worked on some other services that called this service. And this was used for encryption and decryption. We used it to decrypt authentication tokens. Basically, you send a token, get back the decrypted string. It was very high volume, very low latency. To my memory, it was double-digit median latency, like 20 milliseconds, maybe 50 milliseconds. And what we saw was that when the CPU on our boxes was high, we would start to see a lot of cryptex timeouts. And when I was new and first getting onto the on-call rotation, I would see these blips and I said, you know, cryptex is having an issue. I see a lot of cryptex timeouts, therefore cryptex is having an issue. Let's get in touch with that team. And what my colleague said to me is cryptex is very stable. It's very unlikely that they're having an issue. It's more likely that our CPU is high, so we've got a bunch of threads fighting over the CPU, and so we're spending more time queuing, and so we start to see timeouts. And this was very, I did not know that computers work this way. I did not know that usually when I thought about timeouts, I thought that meant the server was slow. I didn't know that could mean that the client was overloaded. But through this example, I learned that and continue to see that in systems I work on today. So let's talk about queuing a bit. When we talk about client-facing latency, it's a combination of your runtime, the server actually doing work, and queuing time, queued up, waiting for a thread sometimes, waiting to get onto the CPU, waiting to get onto the CPU multiple times within the life of a request. And the more active threads that you have per CPU, like the higher your thread to CPU ratio, the more time you're going to spend queuing. And so I think there's some problems in software engineering that you cannot avoid. And I think this is one of them, that when you have a request that comes in, and this is true whether you're like a request response type system or more of a messaging system, if you can process the request, then great. If you can't process the request, you either queue it or you drop it, or back pressure is relevant too in terms of telling your client to slow down. Those are really only your three options, at least that I'm aware of. You process it, queue it, or drop it. And each of these have repercussions. If you drop it, you know, maybe dropping data has a very severe impact to your business, so that's undesirable. Queuing, you know, at some point you're going to run out of memory if you're queuing forever. That also adds to the client-facing latency. Some options are kind of a combination. If you think of a HTTP service returning a 503 with a retry after, that's kind of a drop, but you're also asking your client to slow down. So it's maybe not a permanent drop because they can do a retry, and it's back pressure because of that slowdown. So there's a lot of options here, and I might be missing a few, but I think my point here is that you have to confront this problem. And every one of these is a choice, and every one of these choices has repercussions. And so I think you have to be conscious of that. And so let's move on to talk about metrics a bit. So with regards to operational visibility, the map is not the territory. I think our metric systems are extremely useful, and they help paint a picture of what our systems are doing, but it's an imperfect picture. They're clues, they're hints, they're not reality, they're not the real thing. And so one of the things I ask when I'm looking at metrics, trying to understand a system, is I often say, am I seeing what I think I'm seeing? Like, do I understand what I'm looking at, and does it mean what I think that it means? And so by that, there's a few things specifically I mean by that. For one is, for whatever metric I'm looking at, do I understand how that metric is set by the individual servers or worker processes or whatever? Do I know what it means, and do I know how it's set? You know, is it set at the beginning of the request or the end of the request, or other nuances there? And some metrics, maybe it's not that important. Like, I think requests per second is fairly straightforward, but the more you can know, the better. So another thing here is, do I understand how the metric is collected and aggregated from all nodes? So if you have a 100 node cluster and you're looking at a graph, and the graph has a single dot for each data point, so somehow those 100 data points got merged into one data point. Do you know how that was done? Is it the average of all the data points? Is it the median? Is it the max? Is it the min? Sometimes your metrics tool will allow you to specify that, but it's important to know that when you look at one data point to represent a full cluster, there's some type of editorializing there, and it's important to be conscious of that, especially with regards to things like the min or the max. And so another thing here is how the data is aggregated over time. You know, similar to the way I talked about aggregating a piece of data across nodes, There's also time aggregation. And so if you're collecting data once per minute and you're looking at a data point once per minute, okay, so you know that you have a data point per sampling period. But if you zoom out and now it's a data point per hour, then that data point that you're looking at, how is the individual minute level data aggregated to create that single data point per hour? Was it averaged? Was it min? Was it max? And again, a lot of times your tool will let you choose this, but it's just important to be conscious of this when you're looking at the data to make sure that you understand what's really happening. And so one example of this is we frequently use atomic counters to observe the number of concurrent requests in a system. And in particular, I'm talking about like an HTTP service of some sort. So you have an atomic integer, just for example, you have a try block, you do an increment and get, you do whatever work the request does, then you have a decrement and get and a finally block afterwards. And so I want to talk about an example here of concurrent requests. And so I had a situation where I saw a spike in HTTP 503s coming from a service that I was working on. And so imagine a different graph that showed like a spike in 503s, or imagine an access log that showed that. I didn't create that here. And so I saw the 503s, and I know that we return those when we hit our concurrent request limit. And so I looked at the graph of concurrent requests to try to correlate the two. And so in this graph, and this is just made up data, it's fake to kind of describe the situation. The red line at the top is the max, just so you can see how the individual node level data compares to the max. Then it's two hypothetical nodes here. And so what I saw was strange to me because I knew that we were hitting the concurrent request limit, which was 100, but I didn't see the graph actually get up to 100. You can see there's a little space there between the lines, And I didn't understand this. How are we returning 503 if we're never hitting 100? And after thinking about this for a while, I realized that, you know, we're sampling the data once per minute. You're not guaranteed that at any of those moments, those instants in time when you sample, that you were actually at 100. It's very possible that you were at 96 or 98 or 92 at that moment in time. And so again, like your metric system can't show you like everything that ever happens because you're kind of at the mercy of your sampling period. But in combining my graph of 503s and this graph, I can put together a pretty solid theory that we were hitting 100 just at times in between the sampled points here. And so really what I'm talking about is you want to use metrics to sanity check other metrics where possible. And so with regards to concurrent requests, if I know that my concurrent request went up at 2 p.m., then one or more of these must be true. Either my request rate went up, my latency went up, my instance count went down, which is kind of a subset of request rate going up per node. You have less nodes, same traffic, more requests per node. Or some of my machines are having performance issues, which is kind of a subset of latency went up. Like maybe the machines are just having problems, you know, in AWS, sometimes hardware goes bad, or even noisy neighbor problem or something like that. So either way, if concurrency goes up, one of these has to be true. So let's talk about load generation. In load testing, at least in my experience, the bottleneck in terms of how many requests per second you can have in your load test, it's on the client, it's not the server. I've been a part of a lot of load tests where you run the test and you say, we only got like 20 requests per second. I thought we could do much more, and that's because your client can only generate 20 requests per second. And so to think this through, what's the throughput of a single threaded process which sends requests to an HTTP service with a latency of 1 second? And so my understanding of this is it's 1 second. You send your first request, it takes 1 second to come back. You can't send the second request until the first one comes back. And so you basically send 1 request per second. And if you scale up to, let's say you have 4 threads and 4 CPUs, or maybe 4 processes, 4 CPUs, now you can do 4 requests per second. And you can continue to increase your threads to try to optimize that, but it's kind of a diminishing returns. At some point, by adding threads, your throughput's going to plateau, and at some point it's actually going to go down due to context switching. So one thing you could consider here is using non-blocking I/O as a way of optimizing your throughput per CPU. In terms of how non-blocking I/O works, I'm not going to get into that. The main reason is I don't fully understand it. You can think of it as less threads. You can think of it as callbacks instead of threads blocking on I/O, like I talked about in the diagram earlier. On server side, non-blocking IO, it no longer requires you to have a thread per connection. At least that's my understanding. It allows you to break that link. But I'm not going to get into any more detail than that. And I'm talking about non-blocking IO from the client perspective here as opposed to the server. And so for my example here, this is after I came back to Comcast, but I worked on a project in partnership with Netflix, which was this continue watching A/B test. And so I used to work on the content discovery personalization world. In the on-demand experience on X1, we have this this For You tab, which has this continue watching row, which basically shows things that you've watched recently to allow you to resume. In this A/B test, we injected a Netflix tile with a single Netflix tile with the hope of increasing Netflix usage on X1. And so we had a few, this is the first time we ran a test like this, and we had a few requirements for it. The one was that Netflix selected the device IDs that were going to be allocated, and then they sent them to us. We then had to use those device IDs to look up the account data because we allocated with account information. Both Netflix and us had to allocate the test each on our sides. I think the way we planned it, we only were going to do 6 batches of users in the test. And I think we ended up doing more like 8, but to me, it wasn't worth building an automated allocation system. I thought it was fine to just run it manually 6 times or 8 times. And so that's what we did. And because of the way that we allocate, we use a system called ARS to allocate, and ARS is refreshed in a reboot window, which is over the middle of the night. And so if our allocation time took too long, it crossed that day boundary. It might cause a lot of confusion where not all of the users in a batch got allocated on the same day. And I thought that would just be very confusing, both for us and for Netflix. So my goal was to be able to allocate 1 million users in under 2 hours. And so this is a diagram just kind of illustrating some of the moving parts here. I'm going to fly through this. The Netflix data scientist on the left gives us a bunch of device IDs by uploading to S3. I would grab them, run the allocation preprocessor, which is the system I'm going to talk about here, called a service called XBO to pass it a MAC address, get back the account data. Then I would upload that to S3 to be used by our allocation tool and also by a Looker dashboard that was built by the analytics team. And so the first version I wrote of this script to allocate, or it was the preprocessor, not the allocator. I used blocking IO in Python. It was important for me to use, or I preferred Python because I had a feeling I was going to have to do a lot of hacking on this project. I mean, the whole allocation was kind of a big hack where, being able to just VI into something and change it on the server was much easier than having to do a full compile and like deployment pipeline. And so I wanted to use Python. And for the first version, it was blocking IO. The latency going to XBO is about 50 milliseconds. And so I could do about 20 requests per second, which would take 14 hours for 1 million records, which for me was just way too long. And so I thought about, maybe I could rewrite it in Java, do something with Netty, like how do I get more performance, or do something with just blocking IO in threads or multi-process in Python. But I ended up switching to non-blocking IO in Python, which I had never done before. And it was a little tricky to get it working at first, but once I did, I was able to get the throughput up to 250 requests per second, which allowed me to finish 1 million records in about an hour. And even the 250, that was an artificial limit because I think XBO would only give me 50 CCRs in code big, and that's the furthest that I could push it. But either way, it was over a 10x improvement in my throughput, and which allowed me to meet my requirements for the allocation time and have a single script that I could hack on as necessary. And so I thought this worked pretty well. And so let's move on to talking about when things go wrong, outages, things like that. And so when we talk about code not being thread safe in production, that can manifest a few different ways. You can have inaccurate values due to race conditions. You could have deadlocks, which I forgot to mention here. Those are pretty unpleasant. You can have concurrent modification exceptions if multiple threads try to access the same data structure, or worse things can happen. So my example here, again, is from my time at Netflix. I think this was maybe 2013 or so. And you can imagine, we had a lot of devices in the wild, and we had a fairly standard RESTful API that they fetch their data from. And so on the left here, you can imagine like a single client, like a PS4 or something like that. And having like a sequence of requests it sends to the server. Like it sends the first request, gets some data back, parses it, then sends another request, parses that, then sends like 5 requests in parallel, and then from one of those requests sends another follow-on from those. So it's kind of a compositional nested way of fetching data. The problem with this is that it's a lot of latency. So you have all these network calls. Devices didn't always do a good job of pooling connections. So on some devices, each of those requests is opening a new SSL connection to the server, which, depending where the device is and depending where the closest Netflix data center was that we were running in, or the Amazon data center, that can be the TCP SSL handshake can be a bit expensive. And so this is something we wanted to optimize. And so what we did is we tried to shift all of that logic onto the server, where instead of having that sort of nested compositional access pattern on the client and absorbing that network latency for all those calls, we wanted to could we just make one network call, like make a call just like PS4/home, and then do all of that logic on the server. And so what we did is we built kind of a data access library on the server, and then we had the client teams write these scripts on the server to include all the logic of what data services to call in what order and all that via this like concurrent data model. And so that's what we had, and that's what we put in production. But what happened is in that somewhere in the data model, or the interaction between the scripts and the data model, someone was using a hash map instead of a concurrent hash map. With hash map by itself is not thread safe. And what we saw is that when you get concurrent calls to hashmap.get and hashmap.put, and the call to put results in a rehash, you get this really ugly situation where it ends up in an infinite loop. And the reason for that, is someone explained it to me, was that your hash map is basically just a bunch of linked lists. Each bucket has a linked list, and you can end up, as a part of the rehash, your get ends up pointing to a node in the linked list that points to itself, or ends up in a linked list that points to itself. And so it's basically just an infinite loop at that point. And an infinite loop is basically that CPU is dead. It's just spinning forever. And so we were seeing this bug happen to about 1 CPU every 2 minutes. I made up these numbers, but this is close enough to how I remember it. It was about 1 CPU every 2 minutes. So you can say that's about 30 CPUs per hour. I'm not sure if I did all this math right. And so that's, if you assume we had 8 CPUs per instance, I think we were on like M3 2XLs at the time. We were losing about 4 instances of capacity per hour. And so every 24 hours, we're losing 96 instances of capacity, roughly 100 boxes per day. And assuming we were auto scaling to like 500 nodes at the low point and 1,000 at the top, we're losing 10% of our capacity at peak and 20% at the bottom. And so this is pretty significant. And so this was on a Friday, and it was really important to us that we weren't going to have to do stuff all weekend. Like, we didn't want to have to be constantly watching graphs and manually like terminating instances and doing all that stuff. It was really important for us not to have to do that. And unfortunately, we didn't have a way of detecting the instances that this problem was happening on easily from our metric system. We had a metric system that we could query and do like auto terminations based on metrics, but it was really hard to detect this programmatically. And so what we ended up doing is we pinned our cluster to 1,000 instances, and then we wrote a script and by pinning to 1,000, like we pinned it to our high point, so we basically never scaled down. And then we wrote a script to auto terminate random instances every n minutes. I think it was maybe 2 minutes, maybe 5 minutes, I can't remember. And the goal there was that, for any given random instance, there's some probability that it has at least 1 CPU having this problem. There's also a probability that all of its CPUs are having this problem, but that's very unlikely. And so by just terminating random instances, there's some probability that you just replace a dead CPU with a good one. And so if you do a bunch of math and think about it, you can kind of choosing the right numbers there, and maybe it wasn't just 1 instance every 5 minutes, maybe it was like 5 instances every 5 minutes, I can't remember, but there's some probability that you're going to keep your cluster healthy by doing that. You're basically buying time. And we all slept well that weekend. And I think there's 2 reasons that I like this story. The one is that it's kind of an ugly example of a concurrency bug gone wrong. I mean, this was very unpleasant. And ultimately the problem was fixed, to use a concurrent hash map, but the client team that would have had to do that, they just, there wasn't time on Friday for them to like find the problem and fix it and test it and make sure that it was fixed. We had to give them a little time to figure that out. I think they deployed the fix that following Monday. But our priority as a team was we do not want to spend our whole weekend staring at graphs and having to do stuff. I think it would be very easy to see a problem like this and say, okay, we're going to work in shifts over the weekend. Someone's going to be watching the graphs at all times, and we're going to watch and actively search for the problem and terminate instances where it's happening. We said up front, like, no, we're not doing that. And there were to my memory, there were no managers around that day. I think they were all at an offsite. And so it was just a bunch of engineers saying, how do we solve this? And we prioritized having a normal, relaxing weekend, just doing some type of hack to solve the problem, and that's what we were able to do. We spent more money that weekend because we pinned our cluster high as opposed to scaling down. So definitely there were some repercussions, but we could live with it. And so let's move on to coordination in distributed systems, which I think is my my last topic for today. So I had a job interview back in like 2018 when I was doing my round of interviews before I came back to Comcast. And one of my interviewers used to work at Amazon, and I don't know if he worked on S3 directly or just was familiar with it, but he asked me, how would you design Amazon S3? Which I think is a pretty good interview question. And so when I approach this type of like system design question, I try to start as simple as possible. So I try to start with, let's pretend S3 is just one node. How would that work? And it's fairly straightforward. The node, you store the data likely on disk. You take these different puts for each of these keys. So at some point, that one node isn't enough. Maybe it's because you need more storage space. Maybe it's because you just didn't have the network capacity, or your CPU is too high from taking all of the reads and writes. And so now you have to move on to two nodes. And now you need to have some intelligence around which keys are stored on which nodes. And I think different systems handle this in different ways. I know Cassandra at least used to have, or I think Cassandra used to have like an in-memory table that mapped, I guess, keys to, I think, V nodes and then V nodes to physical nodes. The system has to know this somehow. And so whether it's in memory or whether it's in some type of data storage system, a database, you have to know which key belongs on which node. And so it's simple enough. When you get a write, you look up in that data store which node the data is on, and then you store it. And I'm ignoring things like failover and things like that. But then what happens when you get a request for a new key? Like I've got key 3 here at the bottom. Key 3 is not in this table. How do we decide where key 3 goes? Like how do you know where to store a new key? And this is the part that I got stuck on. And so I think that there's, you can assume that there's some type of list somewhere that has a list of all of the nodes. And you can assume like when you add capacities to the cluster, a node shows up in that list. When a node becomes unhealthy, it gets removed from the list, something like that. And so in terms of options here, there's a few. Like you could do some type of distributed lock. You could use something like Zookeeper, I guess, but that feels kind of slow. And the purpose there would be like request comes into node 2, it's a new key. How do I know that I can consistently make the same choice that node 1 would make? So in theory, if a request came into node 1 at the same time, it would block until node 2 had made its decision. Distributed lock, that would work, it's too slow. You could have some type of algorithm to decide which node the data should go to, but you would need a way to know that the node list that you're operating on is in sync across all the nodes. Like I mentioned at the top, like new nodes are being added to this list, unhealthy nodes are removed. You would likely be like refreshing that on your instances at some cadence, but you don't know between two nodes that they are refreshing at the exact same time. And so to enforce that, you would need some type of coordination there, which is also slow. It was really hard for me to think of a solution that didn't involve some type of coordination, and coordination is slow. So I was kind of stuck. And the interviewer asked me, he said, you're making good points, but you're thinking way too hard about this. What's the simplest thing you could do? And I really couldn't think of it. And he said, well, what's the fastest thing you could do? And I said, you could just write data to a random node. I mean, there's lots of flaws in doing it that way, but that certainly would be fast. And he said that's exactly what S3 did. That S3 chooses a random node to store the data on, and then there's some type of cleanup job that runs every minute or something like that, and like looks at the data and chooses the winner, like chooses the one with the latest timestamp, and make sure that that is consistently stored as the data that, the node that the data is stored on. And that's why S3 was eventually consistent, for that very reason. Now, I had to say was eventually consistent because in doing a little bit of research, I saw that as of December, S3 is now strongly consistent. So maybe they solved this problem in a different way now, or I'm not sure of the details. And if you look at, that was really interesting to me. If you look at the docs for S3 going strongly consistent, they say there's no impact on performance, which violates my understanding of the CAP theorem. You can't increase consistency without also decreasing availability, or decreasing availability usually means increasing latency. My guess here is that their definition, by they I mean Amazon, their definition of impact and performance might be different than yours and mine. You know, they might have, their standard might have been, we had 5 nines of uptime before, we still have 5 nines of uptime. The 6th digit might be different, but the 5 nines are still there. So I'm not sure, but that was certainly interesting to me. And you know, this got me thinking that I still think about this question fairly often. And one of the things that stood out to me is, you know, they ran in an eventually consistent way for 14 years. And I see conversations, I have conversations with teams, teammates, colleagues, et cetera, about eventual consistency. And there's a lot of situations where I feel that people are still kind of afraid of it. And I could see, you know, if you're working on like billing software, or, you know, I work now in messaging, so we don't want to send like a text message to a customer twice. So it's probably worth having strong consistency to ensure that that does not happen, because that's a very bad customer experience. But there's lots of other cases, you know, personalized lists of videos, countless cases where I think eventual consistency is good enough. And so my point here is, you know, Amazon ran that way for 14 years. Are you sure that that choice doesn't work for you? I mean, S3 is certainly one of the cheaper Amazon services, but in that 14 years, they made a ton of money running in that way. And I think as a general policy, you know, Amazon and us, we have very different businesses, but I think, you know, if Amazon is fine just choosing a random node and writing data to it and doing a cleanup every minute, shouldn't that be good enough for us also? Like I can imagine going into the architecture channel and proposing that solution and having, you know, 20 different nerds telling me how that's not a good enough solution. Amazon ran that way for 15 years and made billions of dollars. I would suggest we revisit how we define good enough. So that's all the main topics for today. I'm going to go through some closing thoughts here. So for one, do the simplest thing that could possibly work. Write data to a random node and clean it up later. That might be good enough for your use case. Just to having a single activity lock and not having to get really deep into multiple read-write locks, that might be good enough for your system. And to make that decision, you have to know what your performance and capacity requirements are. You know, how much concurrency do you need to support? How many requests per second? What are your storage requirements? Really try to learn more about those. If it's unknown, you know, dig into it a little bit, because once you know those, it really allows you to make better decisions in terms of your system architecture. Queues are everywhere, and this is especially relevant when you're trying to debug issues where your latency is higher than you want it to be, which is you know, a pretty frequent problem. I think when we hit those situations, we're sometimes quick to start, you know, adding indexes to databases, or you know, scaling up services, or, you know, optimizing blocks of code, when, you know, those are not bad things to do, but in a lot of situations you've got stuff sitting in a queue because your queue is configured to be too large, or, you know, there's just so many places. It could be the CPU queue, it could be a thread queue, it could be a queue, you know, you're waiting to get a connection to an upstream system because your connection pool is configured too small. There's all these different spots in your application where queues can be filling up and creating like silent latency that you're not even really able to observe. So I would say when you hit these problems, when you're trying to diagnose latency problems, think about everywhere that there could be queues and something could be blocking, waiting for a resource, and look there first. Metrics are a map, not the territory. So again, our metric systems are invaluable, but they can't tell you the whole story. It's giving you clues. It's not painting like a perfect picture of what your system is doing. I think the hardest problem in software engineering is knowing what your system is doing. I think our metric systems, they help with this a great deal. You know, we have logs, we have metrics, but none of these things can tell you like exactly what your system is doing at a particular moment of time. They're clues, and they help you to kind of formulate and like triangulate on a theory of what your system was doing, but it's just that, it's a theory. In a lot of situations, having a good theory is good enough, but it's important to be conscious of that. And I would say last here, comprehension is a journey. You know, back to one of my first points, this stuff is hard. It's hard for me, at least. There's lots of things that I still realize every day that I do not understand. I thought I understood it. I realized, wow, I really don't understand it that well. I need to do more research. And I think especially with regards to concurrency and queues and latency and all these things, it's really just a lifelong journey that there's so much to learn, and there's so many corners, there's so many edge cases that I think for me, I just have to embrace it, embrace the fact that I'm going to feel stupid sometimes. I'm going to say stupid things in meetings and be corrected, but the goal is to learn. The goal is to get better at it. And I think if you keep at it, you'll be successful. And that's it for today. Thank you.
Thanks, Matt. I'm not seeing any questions in the chat, but one comment, just how great this talk was. So thank you so much.
Oh, thanks for listening. Yeah, and you can send me questions on Slack, send me an email, however you want to do it, if you can't think of any right now.
I do see one question that came through. Synchronization in Python across different processes, anything in mind?
I mean, that sounds like something I wouldn't want to do. I think Python, I thought there might be like some libraries that can do that. I thought there was a library or a module called multi-processing, but in the end, like the synchronization is the tricky part. I would actually encourage you to look at non-blocking IO, because they have like a queue data structure that allows you to synchronize between tasks, which in terms of concurrency is very similar to multiple processes. So I think that might be the one and only situation where non-blocking IO is easier than doing it a different way.
Thanks for that. That's the only question that I see.
Okay. So
if there's nothing else, I think we can wrap up. And thank you so much for the time.
Yeah, thanks everyone.
Bye-bye.